So today we're gonna work on our worksheet number 6 about arc length and some kind of integration by parts. So let us start with question 1. Find the length of the curve y equal to ln of square root of x minus x squared. And for x from 1 to e. So we'll write out the formula first. Formula that is L equal to this square root of 1 plus, and that is dy over dx or dx over dy, depending on situation. And because in this question, the curve is expressed in terms of x, so we will do the integration in terms of x. So we use dy over dx instead here. Dy over dx squared. And because of that, we need to also write dx here, because the integration is in terms of x. And also my bound should be the x bounds. So it's from 1 to e. And after this, we plug in. So plug in this thing, 1 plus. The derivative of this, it's 1 over 2x plus x minus, it should be x over 2 squared. And I use the chain rule in here for this guy. Right? Chain rule is in here. Used. Dx. And we open the bracket to simplify the expression. And we have 1 plus. This is 1 over 4. Let me write it this way. This thing squared plus x over 2 squared minus 2 times 1 over 2x times x over 2. Okay. And this is a very common pattern that we will see in the integration like this. The third term here, this term, is actually a constant when 2x are cancelled out. And we can combine this with the 1 here. So this becomes, it was originally negative 1 over 2. But after plusing 1, it becomes positive 1 over 2. So we can regroup these terms together to create another perfect square. And the perfect square we created here, it's just the same perfect square with the sign in between replaced by the opposite sign. So it becomes now, here it becomes plus x over 2 squared. And also write out the expression here for you in the expression in general. That is 1 plus this 1 over 2 a minus 1 over a. It's a reciprocal. Okay, square is equal to 1 over 2 a plus this thing square. When you do the algebra, just open the bracket, you will see this this formula, and we use this here to kind of change the perfect square. Okay, change the perfect square. That is from here to here. Use this step. And later on, we're gonna use this square, perfect square we have just created, to cancel with that square root. So we have from 1 to e, is 1 x divided by 2 dx, this one. And it can be easily integrated. And the final answer is 1 plus e squared divided by 4. Okay, so that is our question 1. Find the length of the curve. Should be very straightforward except for this formula part here. Now let's go to question 2. Question 2 is here. Set up but do not evaluate an integral for the length of the given curve. Okay, so it's actually the same type of question as the question 1. We follow the formula to write the integration here. It's 1 plus, right, dy over dx, or dx over dx over dy, depending on situation. But in this case, the function is expressed in terms of y, so we need to do the integration in terms of y, okay? In terms of y. So now we have dx over dy square dy. And because the integration is in terms of y, it means that we need to find the bounds about y. The given bound is the bound with respect to x. We couldn't use that because now the integration is in terms of y, so we need to find the bounds in terms of y. Now how do we do that? We substitute this 0 and 3 into this expression here to find the corresponding y value. Okay, so that is when x is equal to 0, we have 0 equal to y3 plus 2y, right? And if you solve this, you have the corresponding y value, that is y equal to 0, okay? And that is our lower bound, 0 here. And for the upper bound, when x is equal to 3, we have (3) equal to y3 plus 2y, and you solve this, right? And gives you y equal to 1. So my upper bound here is 1. After finishing this, I can plug in 0 to 1. This is 1 plus dy over dx, that is derivative, so I have 3y square plus 2 bracket square dy. Okay, that is the integration. We do not need to evaluate it. We just need to write out the expression. So that is about the question A, 2A. And you see that the only one difference here is finding the corresponding bounds, because sometimes that bound is not given. You need to find it yourself. And after this, let's move to question B. Same way, integration, right? 1 plus is either dx over dy or dy over dx. But in this case, it's easier or more convenient to express the function in terms of y. We just need to, for this one here, move the y to the other side. So you have x equal to y squared minus y. Right? Now, we know that we need this dx over dy squared. And the equation is in terms of y. And now we need to find the corresponding bounds of y, right? So we know that the curve is from P to Q. Now let's take a look at the y coordinates, right? The y coordinate should be from 1 over 2 to 1. Okay, so 1 over 2 to 1, put in the bounds. Now we finish, right? And then the last step is just to plug in. It's 1 over 2, 1 here, 1 plus this derivative, the green derivative here. Right, this one you plug in, we have 2y minus 1 bracket square dy. And also very simple and straightforward. That is our question 1 and question 2. They are all the same. Okay? How were you able to get y3 plus 2y again? No, we're not using y3 plus 2y. We use this one, x equal to y squared minus y. The green thing there. Okay. Now let's move on to question 3. Set up but do not evaluate an integral for the area of the surface obtained by rotating it about a specific axis. So when it comes to this question, lots of people get confused. They think that sometimes in terms of y, sometimes 2 pi x, 2 pi y, and we don't know when is which. So let's take a look at this. Firstly, the formula says S is equal to 2 pi x or 2 pi y, right? And there's something here, 2 pi x or 2 pi y. So this thing is to be filled. And this is 1 plus. This bracket is either dx over dy or dy over dx. And another symbol, the differential sign, the dx or dy in the very end. So now we take a look at the condition in the question. If the rotation is about the x-axis, that means your radius has to be y, right? So when the radius is y, the circumference has to be 2 pi y. So we need to fill in the y here because of that. And for the other part here, it could be either dx over dy or dy over dx. It depends on your preference and also depends on the expression of the curve here. You can write dx over dy, but it might be more difficult to figure out the derivative later on. Okay, so in this case, for my convenience, because it's easier to write the function, the derivative in terms of x, so we will use dy over dx instead of dx over dy. Okay, and now this is dx, sorry. So it should be like that. And since the integration is about x, we need the bounds also be about x. So it's from 0 to pi over 2. Okay, now we kind of plug in after this setup, 0 to pi over 2, 2 pi y. Okay, y is our sine x plus cos x. And this is 1 plus dy over dx, which is cos x minus sine x squared dx. And that is our integration. Okay, we do not need to evaluate it, just set it up. And you can see that the only difference is that we have one part here, right, that's 2 pi something. And we know this part is fixed by the question. You cannot change it, right? It has to be that way according to the question. But for the other part here, this part is up to you. Okay, this part is up to you. If you choose the right one, it's convenient for you. If you choose the wrong one, it might be too difficult for you. But this one is not fixed. This one is up to you. Okay, that is about this rotation. stuff. And let's take a look at B. Now S is equal to integration, right? And I look at my question, it says about y-axis. So I know my radius should be x, right? And this should be 2 pi x. So it's fixed, this part 2 pi x. 2 pi x here. And now the other stuff, 1 plus, should it be dy over dx or dx over dy? Now let's take a look at my expression. It's more convenient to write the derivative in terms of y, right? So it's better to write in terms of y. That is dx over dy. And because it's in terms of y, I should have dy here. So I need a bounds for y, which is already given. That's very nice. So from 2 to 7 to 2 to 7. And now the final step, just to plug in 2, 7, 2 pi, right? X is our tangent, -1, y squared plus 1. That's 1 plus dx over dy. I will use the chain rule. Okay, the chain rule applies here. That becomes 2y divided by 1 plus y squared plus 1 squared. Again, square dy. The chain rule. Okay, so that is our integration. Set it up. We don't have to evaluate it, and you see that is completely the same as question A. You have this part fixed, right? And this part is, another part is up to you here. Depends on your preference and convenience. Okay, so that is question B. Now let's move on to question 4, which is also the same, I think. Find the area. Okay. Now follow the same format. The surface area S is equal to integration, right? And then I know this is about the x-axis, right? So this part is fixed, 2 pi y. I should write 2 pi y here. And the other stuff, that is this square root 1 plus. Should it be dx over dy or dy over dx? It depends on you. Okay. And I see that it's easier to express the function in terms of y. So I write dx over dy square, now dy. And the bounds should be in terms of y. So I use the y bounds here. That is from 0 to 1. Okay. Now it has been set up. And now we go through it. 2 pi y. This 1 plus dx over dy, that's the derivative of this function. That is 2y, right, squared dy. And to evaluate this function, we need some kind of substitution, right? So think of letting this 2y go into the square root. This 2y goes into the, not the square root, the differential sign, I should say. And we also open the bracket. Open this bracket for y squared. So I have now, this is y squared here into the differential sign. And then I compare the thing inside the square root and the thing inside my differential sign. They are different, right? I need a 4 So I place a 4 here. And I also need to put another 1 over 4 here to kind of cancel with that 4. Okay? And still I'm missing something in the differential sign. That is the constant 1. But we know that there's no cost to put another constant in the differential sign because the derivative of any constant is 0. So it doesn't hurt me to plus a 1 here, right? Plus a 1 here. Now after this, I see that the stuff inside this square root and my differential signs are the same. And now I can let u equal to 4 the square plus 1. Okay? And the integration now becomes from this, it should be square root of u du. And I need to use the bounds for u, okay? The corresponding bounds for u. When y is equal to 0, u is equal to 1. So the low bound, new bound here is 1. And for the upper bound, when y is equal to 1, we have u equal to 5. So the new bound here is 5. Okay, finish this new bounds and go through this computation. The final answer is complicated. That is pi over 6 times 5, 3 over 2 minus pi over 6, something like that. So that is our question A. You see that the only difference here is when computing this integration, sometimes we need to apply the substitution. Okay, so the substitution plays a role here. After this, let's go to question B. Integration is equal to this is about the y-axis, right, the rotation. So I need 2 pi x here, so I write 2 pi x. Okay, and the other stuff here, that's 1 plus. It should be dy over dx in this case, obviously. So dy over dx square in terms of x now, okay? And I need my x bounds, that is from 1 to 4, already given. And now it has been set up. And we can now plug in, that is 2 pi x 1 plus dy over dx. What is dy over dx? We simplify this a little bit first. So this y is equal to this one, okay? Simplify it, becomes, so split the sum, I have x to the negative 1 over 2 plus 5 times x to the 5 over 2. Okay, go through the computation. And its derivative is obviously negative 1 over 2 x to the negative 1 over 3, negative 3 over 2, plus this 5 goes down. Oh, this is 1 over 5 instead. Cancel with that 1 over 5. So I have x to the 1 over 2 times x to the 3 over 2. Okay, so it's this one here. And you can write it that way. This is x 3 over 2 minus x negative 3 over 2. And then I'm gonna put it here. Okay, put this thing here. So 1 over 2 x 3 over 2 minus x negative 3 over 2. Bracket, square, and dx, sorry. Now remember the pattern we talked about at the very beginning. This thing is gonna be in used. Which one? Oh, this one. Right. This one is gonna be in use. 1 plus 1 over 2 times a minus the reciprocal of a, right? Now this one is a, and this one is the reciprocal of a, right? So you're gonna see that very often, right? And this is gonna be turned into the perfect square with the sign in between replaced with the opposite sign. Okay, so now I have this equal to 2 pi x. This is going to be replaced with 1 over 2 x 3 over 2. Now this time it's plus, right? Because of the same reason. If you think it's confusing, then you can open the bracket and go through those computation and you will see it. Okay. And as before, this square root is gonna be cancelled with the square inside. So I can remove that square root and the square, and I'm left with this guy only. Okay, and this is very easy to compute just by the power rule, right? You multiply things through and then do the integration. And our final answer is complicated. That is 268 divided by 7 times pi. Okay, which is not very important. The important thing is how do we set up the integral. And there's a technical stuff here in one step. That is to cook up that kind of perfect square. And apart from these, everything else should be very obvious to see. That is our question B, 4B. Now we see this common thing about question 3 and question 4, right? Yeah, it should be intuitive right now. So let's go to the last part of the question. Evaluate the following integrals using integration by parts. So start with this one. Oh, this one's here. This type of question is like the substitution question. How do we know which kind of substitution we need to use in a given situation? It's hard to tell. It depends on experience, depends on your sense. So that is why we need lots of examples, or lots of practice here to help us to acquire that kind of sense. So for this one, an important observation is that you need to notice this secant square is the derivative of the tangent x. Okay. Once you sense that, you put that into the differential sign, and now you create this one, x d tangent x. And then by the integration by parts, we kind of write out the product, and then minus the integration by switching the positions of these two functions. So switch the tangent x and x. So x goes into the differential sign and tangent x goes out. So that is this one here. Now it's easy to figure out this integration. You can look up the formula sheet. There's the integration in this formula sheet. Or you can use substitution to work it through. Okay, that is sine x over cos x dx, and you let this sine x go into the differential sign. Okay, so that becomes 1 over this d negative cos x. And these two negative signs, they're gonna be cancelled. Okay, cancel, and you're left with x tangent x kind of plus this cos x d cos x. Substitution tells you need to let this be u. Okay, this guy is gonna be your u, this guy is gonna be your u, right? So the final answer is x tangent x. That's the log function, log u, right? And u should be replaced with cos x, an actual absolute value. Okay, and at the end we plus c. Okay, that is integration by part with a little bit kind of substitution. Our question A. Now move on to question B here. 4y squared e to the 2x, right? You can choose to let this x squared go into the differential sign, or you can choose to let the other one go into the differential sign. Which one is correct? You should try it out, right? And I can tell you that if you let this go into the differential sign, you kind of increase the power, which will make the question more complicated to solve instead of making it easier. So after trying, you will know that that is the wrong way to go. So the right way is to let this go into the differential sign. And the only way to know the correct choice is by trying. Just continue to try. And now we have this 4x squared d of this negative 1 over 2 e to the this negative 2x. That is the integration of that thing we put into the differential sign. Now we take care of the coefficients, kind of cancel out this 4 and this negative 1 over 2. Okay, take care of them. Now we have negative 2 x squared d e to the negative 2x here. Now by the integration by part, we can write the product minus the integration by switching the positions of these two functions. So this thing goes out and the x squared goes in, right? Switch position. Switch position. And that is our new integration. And now negative 2 x squared e this minus this is e to the negative 2x and 2x dx. Okay, now we still need to work on this guy, right? But you see that now this guy is much simpler than the previous guy here, right? You previously have the 4x squared, but now you only have x to the 1. So the power has been decreased. So we know that this is making things easier, which is the right way to go. Now we try to figure out this guy. Okay, try to figure out this guy here. So now this guy, right, figure this out. 2x dx, right? Obviously we need to use the integration by part once again. And then we're gonna let this go into the differential sign. That gives us 2x d negative 1 over x 1 over e to the 2x. And we take care of the coefficient. So negative of this x d e to the negative 2x. Okay. And then we apply the integration by parts once again. Negative of the product, and then the new integration by switching position. Right. And now we have negative e to the 2x minus, for this one we know it very well, that is 1 over 2, negative 1 over 2 e to the negative 2x. Okay, so that is that guy there. And finally we plug in this guy back into the expression here and write out your final answer, which is let me see, which is the final answer negative 2x squared e negative 2x, right, minus 2x e to the negative 2x minus e to the negative 2x, and plus c, which is complicated. But the idea should be very intuitive here. We use the integration by parts, right? We need to choose the correct thing to put into the differential sign, which comes with experience and practice. And sometimes we need to use the integration by parts not only once but twice, or maybe three times. Okay, so that is our question B, integration by part twice. Now maybe take a look at question C. Okay. Question C here. Question C. We apply the integration by parts directly. Just switch the position. Okay, so write out the product here. Minus new integration by switching position. ln this one plus this. Kind of switch position. And after we simplify the second integration, we have x. Okay, let that thing go out and apply the chain rule, that is 1 over this x, this thing times 2x dx. Okay, so we have this one here. And now we simplify the expression. This is ln times x minus 2x squared, this x squared plus 1 dx. We have gotten rid of the ln stuff. We just need to take care of this one here. Take care of this one. So this is a rational function, right? The hints there says you kind of simplify this. Just split this term in the numerator so that you can create something where there's only constant in your numerator. So let me write this out. This is equal to this 2x squared over x, right? And I kind of cook up something and the top is x squared plus 1 minus 2, right? Divided by x squared plus 1. And now I can split this terms on the top into two parts. So I can split the division. So I have 2 minus 2 x squared plus 1. This is very common technique to use. Okay. So now I have this one here becomes integration of 2 minus 2 divided by x squared plus 1 dx. Okay, which is equal to negative 2x plus 2 tangent negative 1x. Okay, that is in your formula sheet. Oh, I mess up with the sign. This one should be positive, this one should be negative. This one should be positive, this one should be negative. Okay, and finally we plug this in back into the previous expression. Okay, and the final answer is equal to here ln x squared plus 1 times x minus 2x plus twice tangent negative 1 x plus c, where c is any constant. Okay, so that is our question C. A little bit technical stuff in between after the integration by parts. So it's about time, so I don't think I'm able to go over more questions. So do you have any questions about these stuff? Any questions?